Welcome to this video on separable ODEs. In this video, we're going to be looking at three things. First of all, the form of a separable ODE and how to identify ordinary differential equations as separable. Two, a general solution technique and methodology to solving a separable ODE. And three, a specific application of this method with an example. All right, so let's look at the form of a separable ODE. Separable ODEs take the form of this equation here in this box, where the derivative dy and dx is equal to the multiplication of a function of x and a function of y. And the reason why it's called separable is because you can separate out the derivative in terms of y and x and have it be the multiplication of these two functions together. There's no cross terms or interaction terms of x and y. There's just a function of x, and that function of x is multiplied by a function of y. Of course, as this is an ODE, the idea is to solve this equation to determine the unknown function y that is dependent on x, and we have information about this unknown function in terms of the derivative dy and dx and some equation of variables of x and y. Alright, so let's take a look at some examples of ODEs and determine whether they are or are not a separable ODE. So function number one, dy on dt is equal to y multiplied by 1 minus y. And the question is this separable? So we've already got on the left-hand side our derivative, and the right-hand side we need to think, can we represent this as a multiplication of the variable of interest, y, and then the variable that it depends, the function depends upon, which in this case is t. And here we can say that, yes, this actually is separable, because g of y is equal to y multiplied by 1 minus y. That is strictly a function of y. And then our f of t in this case would just be 1, the constant one. So the answer is yes, this is separable. Some people might get tripped up by this because f of x is equal to 1 and there's no x inside of this function. But this definitely is a valid function of x, even though it is a constant function with input x. Okay, example number two, dy, this would say dy on dx is equal to e to the power of x plus y. Is this separable? So in order to understand whether this is separable, we need to expand out that exponential, and that is equal to e to the x multiplied by e to the y. And writing in that form makes it pretty clear that it is indeed separable because it's f of x multiplied by g of y. So yes, it is separable. Number three, y prime is equal to e to the power of x plus y all squared. So if we expand that out, we get x squared plus 2xy plus y squared, and that becomes equal to e to the x squared multiplied by e to the xy multiplied by e to the y squared. And in this case, we're stuck because in this middle e to the xy, this middle exponential, we have a cross term xy, and so we cannot clearly define our f and g functions in terms of x and y to have them separate into the multiplication of two distinct functions. You can't put this into fx or gy and successfully have this multiplication together. So that's not going to be separable there. Okay, our fourth example, we have y dot, so the derivative of y is equal to ty plus y on t squared. And if we are looking for this form, we'd want to separate things into g of y. So if we factor out y, we have y multiplied by t plus 1 on t squared. And of course, this is then going to be separable because we have the y function multiplied by the t function. So yes, that is separable. And then our last function here, we have ty plus y squared. If we were to factor out the y, we have y multiplied by t plus y. And in this case, we have a problem because that t plus y is now a function of both t and y, not distinctly t. And so we cannot separate it out. So that last one is not separable. Okay, so of course it's important to understand how to identify ODEs as being separable, because if you want to use the solution methodology on the ODE, you need to successfully classify it as one, otherwise the process is not going to work. And these ODEs that can be represented as a separable ODE can be solved in a specific way. So let's derive our solution technique for a separable ODE to actually understand our approach and how we want to solve these ODEs. So the general form is given by the derivative being equal to f of x multiplied by g of y. And the reason why this is so useful as a form is that we can divide both sides by g of y to give us dy on dx. 1 on g of y multiplied by dy on dx equal to f of x. And now when we integrate both sides with respect to x, what ends up happening for us is that this is going to essentially give us the integral of 1 on g of y with respect to y is equal to the integral of f of x dx. So we now have fully separated our ODE into an integral with respect to y on the left-hand side and an integral with respect to x on the right-hand side, and functions that depend upon only y on the left and only x on the right. And that means that we can successfully do these integrals by using our standard direct integration techniques. So when we get down to this step here, we can go ahead and just integrate the left-hand side and the right-hand side with respect to their fellow variables. And there's no issues because our functions are aligned with the integral of interest. So here we've got x on the right and y on the left. And of course, that is why it is called a separable ODE, because you can separate it onto left-hand side and right-hand side in this format. So once you get to this part here, you'll get some overarching function here in terms of y and a different function in terms of x on the right-hand side. And the last thing you need to do is completely rearrange that into y of x. And that might not actually be possible depending on what your integration looks like on the left-hand side in terms of y. So this solution technique might not always work as well as you'd like it to, but you can try your best in the rearranging process and see if you can get a explicit function of y in terms of x. And at the very least, you can get a implicit function of y in terms of x. Okay, so let's look at an example of this. So let's look at the example. Dy on dx is equal to x divided by y. So is this separable? Well, the answer is yes, because we have our derivative equal to the function x multiplied by the function 1 on y. And we can now have this in the separable form to just proceed with our integration as we worked out above. So this ODE is equivalent to y dy on dx is equal to x, and then integrating both sides with respect to x. Gives us this. And that gives us 1 on 2 y squared plus c is equal to 1 on 2 y squared plus d, and c and d is some real number. And if we move c across to the right hand side, we just get a new real number that doesn't matter. And if we multiply everything, sorry, that should say 1 on x squared. So that should say 1 and 2 multiplied by x squared. And if we multiply both sides by 2, we get y squared is equal to x squared plus k. So k here is just equal to d minus c multiplied by 2. And then that takes y as plus or minus the square root of x squared plus k. And there we have it. Any function of this form will satisfy the original ODE dy and dx is equal to x on y. And we can verify this because if we were to take y equal to the square root of x squared plus k, and then differentiate that. So let's just quickly do that to finish this video. So if y was equal to the square root of x squared plus k, then dy on dx is going to equal to 2x on 2 square root of x squared plus k. That's just using our chain rule, because that here is equal to x squared plus k to the power of 1/2. So the half will come out to the front. That will go to minus 1/2, which brings it down to the denominator as a square root. And then the chain rule inside gives us 2x out the front. So that is equal to this. And of course the 2's cancel out. And then that is x on y, because this thing here is our y. So that is valid as a solution for our initial ODE. Right, so that's what a separable ODE is. Any ODE that can be represented in this form, and we just separate out the ODE and integrate both sides with respect to x. And fortunately, the nature of this equation is that the left-hand side will then be integrating with respect to y and be a function in terms of y. And we can perform that integration directly and then solve for what y actually is. All right, thanks for watching this video.